Hi, this is Michelle Miller, and today I'm going to be talking about climate change. And I'm also going to be ozone depletion, and I want to make the point that these are two very different things. And climate change, we're in the midst of trying to figure out how to deal with it. But in terms of the ozone depletion, we have actually found a solution, which included changing our habits as humans and ceasing the release of certain chemicals into our atmosphere. And the ozone hole seems to be on the mend. And so one is kind of a bad story, one that we do not know the end to, and the other one is considered to be a success story. Okay, so we're going to talk about climate, and it's really important to realize that climate is a shift in the long-term changes of the weather. So it's not like the weather on a particular day at a particular moment where we're talking about precipitation, the amount of rain or snowfall. We're looking at trends, and so this is a change in the patterns of weather over the long term. Okay, so obviously there have been changes in the climate previously, and the lead-in story to this chapter is talking about Greenland. And it was talking about Norse or kind of Viking settlements in Greenland and how they were very common during the 984 AD to the 1400s. And then in about, with Greenland, there was a cooling. And it came at about 2050 after death AD. And this trend, what happened is that the temperatures got cooler, the seasons got shorter, and the people that lived in this particular area started to move away because of the change in climate. So there was climate change because the climate cooled. And so by the 1400s, there were very few people living in that environment, Norse people. However, there were still Inuits, so it's still indigenous native people that lived there. So the point being is that the climates do change over time. What we're talking about in terms of climate change today is climate change that is caused by humans, and that tends to be more rapid than what we see historically when we look at climate in the past. So if we look at the difference between climate and weather, so this would be the definition, would be the atmospheric conditions in one particular place at one point in time. Right, so this would be like looking at the temperature and precipitation and wind speed and barometric pressure and the cloud cover on a particular day in a particular area. And so when we talk about weather, when we're looking at the news, this is what we refer to as the weather, right? So we're looking at the amount of rain over a given area. And that is different from long-term patterns of weather, which are referred to as the climate. Okay, so when we talk about the climate, one of the things that we have to talk about is the way that we obtain energy and the way that we get rid of energy. And so for the vast majority of the ecosystems on the planet, the energy that comes in is from solar radiation. So we do have in the middle of our planet a core of energy, and in some cases this bubbles up as molten lava, and it also has deep sea thermal vents, which release heat and methane and hydrosulfuric gas. But when we're talking about the heat balance, we're generally talking about solar radiation. So solar radiation is coming in, and there are different things that affect the amount of solar radiation hitting the Earth. So factors determining how much hits the surface. So one obvious factor would be, for example, the cloud cover. So clouds can reflect the energy back into space. And so when there is stormy and there's lots of clouds, we get less heat hitting the surface. And we all kind of know that when it's cloud cover, it tends to be cooler outside. So we can also look at the particles that are in the atmosphere. Oops, particles, I spelled that wrong. Particles in the atmosphere. And these are what are referred to as aerosols. So these aerosols are liquids or even solids that are suspended in the atmosphere. Oops, liquids or solids suspended in the atmosphere. And so one example of an aerosol would be volcanic ash. So when we have major volcanic eruptions, this sends aerosols, bits of ash into the atmosphere, and this can actually lead to cooling. So this is actually out of human control, right? So volcanoes erupt periodically over time, and so we never know when that is going to happen. But in the past, we've had these giant volcanic eruptions that have dramatically changed the climate over time. Another thing that affects the aerosols is the emission of sulfur dioxide. So sulfur dioxide forms an aerosol, and it is actually emitted when humans burn fossil fuels. So this could be produced during the burning of coal. So it is actually not considered to be a greenhouse gas, rather it is an aerosol, and actually this actually serves to cool the planet. So the more sulfur dioxide we have in the atmosphere, the cooler it is. But the downside is to this is that this also causes acid rain. So there has actually been a push to reduce the amount of sulfur dioxide that's being released into the atmosphere. And that has actually reduced the amount of acid rain. And acid rain can do really damaging things to terrestrial environments, but also to aquatic environments. Okay. So when we look at this heat balance, we have heat coming in, and you'll notice that we have these high energy shortwave radiation that it comes into the atmosphere, and then coming out of the atmosphere, we have some heat loss. And so this actually is long wave radiation that is radiating back out. And some things that prevent that radiation has to do with the greenhouse gases. And so what these are right here are these examples of the examples of the greenhouse gases that are going to prevent heat loss. So we have heat coming in and heat being radiated back out. So the greenhouse gases absorb energy and prevent it from leaving the Earth's surface. Prevent heat, we'll put, from leaving the Earth's surface. Okay, so that's the heat balance. So it's a system, things flow. Heat, energy flows into the Earth, and energy needs to flow out of the Earth. And if we change or we disrupt the amount coming in by cloud cover or sulfur dioxide, then we're going to cool the planet. But if we prevent the amount leaving, then we're going to heat the planet up. Okay, so this is just an example of a volcanic explosion, right, that is releasing particles into the atmosphere that are going to actually create kind of a cloud cover so that not a lot of solar radiation is going to reach the planet's surface. Okay, so if we look at some of these greenhouse gases, so this would be carbon dioxide. Methane is CH4. And these are actually things that, in terms of carbon dioxide, this is a product that we breathe out. And so you say, well, how can that be so bad? Because this is something that is not toxic to us, that we are actually producing and breathing out. But it's its effect in the atmosphere, in that layer of the atmosphere, its accumulation in the atmosphere can be damaging. And then this is methane right here. And methane is produced during decomposition. And so we have methane gas that can be produced during, for example, when things start to break down. And actually, sometimes our flatulence, or the gas that is produced by the bacteria in our digestive tract, also releases methane into the environment. And sometimes methane escapes from swamps. And the tundra is believed to be emitting methane because it is starting to thaw. And so methane kind of can be stored and then released. And then nitrous oxide is NO. And then we have these chlorofluorocarbons. And if we look at the relative forcing, so the radiative forcing, this is how much it affects the atmosphere. So you notice that nitric oxide has a relative forcing of 270, but its atmospheric lifetime is much less than the carbon dioxide. And then methane has a much lower radiative forcing, and its lifetime is less. But the carbon dioxide seems to live in our atmosphere for long times before it gets broken down or taken back up. Okay, so if you combine these two ideas of how much energy or how it changes the heat balance, this idea, with its atmospheric lifetime, then you can look at its a contribution to heat gain. And so carbon dioxide is much worse than the methane or the nitrous oxide, even though because it exists, or it stays in the atmosphere for so much longer. Okay. And notice that these volcanic sulfates and then the anthropogenic, so this actually means that it's produced by people, and I think there's an O missing in that for some reason. This actually decreases the radiative force. So this is, the radiative force is the amount of heating that is taking place on the surface. Okay. So we know that the climate has changed over time. And in fact, the last ice age was about 18,000 years ago. So this was our last major ice age. And the way that we are able to historically study the climate is that we can, so if we look at things that we study when we're studying historical climate, one of the things that we can study is that we can go in and we can drill and we can get these ice cores. And the ice cores have in them stored levels of CO2. And so if CO2 is high, then that is going to mean that the temperature is warming, and CO2 is low, then that means that the temperature is decreasing. So let's see if I can go back up here. So ice cores. And you can get these in the Antarctic where the ice can be miles deep, kilometers deep. In the ice cores, you can measure the amount of CO2. There's other things that other information that you can measure. You can also measure the amount of a certain type of oxygen, and this oxygen is less likely to be present if the temperature is warm, and it's more likely to be present if the temperature is high. So if we look at these, this historical, what we see is that increased CO2 levels lead to warming. And decreased CO2 levels lead to cooling. Now, the amount of CO2 in the atmosphere is actually predicted to change based upon the amount of light that is actually hitting the Earth. And so when we look at this, we call this, this just actually shows carbon dioxide over thousands of years ago. And so notice that there is natural fluctuations in the CO2. So in periods where there's low CO2, that would be where it is cooling, and periods where there's high CO2, that is where it is warming. So there's natural fluctuations. So this is the example of the Ice Age, where we have most of North America, where we would live, actually we're kind of right on the edge there, but a lot of North America was actually covered by an ice sheet. And this is actually the Ice Age that caused extinction, is believed to have caused extinction of the horses and the mammoths and some other species that we no longer have in the North American grasslands. Like, for example, we used to have a North American cheetah, and we used to have a North American camel and rhino, and similar to those types of organisms that are seen in the African savanna. But during this time of cooling, it caused a lot of species extinctions. You'll notice Greenland was all covered with ice now, or back then as well. Okay, so when we talk about anthropogenic climate change, this means human caused. So over time, what we see in the climate is that we see that there is a forcing of the climate above what would normally be considered normal in terms of temperature, okay? So solar insolation is the amount of energy that is hitting the surface of the planet or reaching the surface of the planet. Notice how that fluctuates, and that fluctuation is believed to be due to the Earth's orbit. So this is due to changes in the Earth's orbit. So when we had that ice age, there was a change, was believed to have been a change in the Earth's orbit that actually caused there to be less solar radiation hitting the planet. And so you can notice that this fluctuates on a regular basis, kind of up and down, right? But what we see here is that there is a energy, this net forcing, is the amount of heat that is staying in the atmosphere, as opposed to the amount of sulfuric emissions, which is decreasing because we actually cleaned up the air and we're not producing as much solar emissions. And then you'll notice that the volcanic activity seems to be pretty random as well. So we have this major kind of, well, a minor actually in terms of global, but in Hawaii, that's releasing a little bit of ash into the atmosphere. And so that's also really releasing sulfur. So that would be predicted to cool that particular area. Now, the thing about the greenhouse gases is that they do not stay in the place that they are produced. They actually get mixed into the atmosphere. So it's not like a big city has more greenhouse gases above it. It does have more smog or more pollution down on the surface of the planet, but the greenhouse gases are actually up in the atmosphere. And so because of their long lifetime, their long lifespan specifically, carbon dioxide gets mixed. And so up on the North Pole, we have actually quite a bit more warming, but we have just as much CO2, even though that's not where it is being produced. So CO2 being produced in the lower latitudes is actually causing the buildup, well, not the buildup, but it's causing CO2 to be high everywhere on the planet, including the polar regions. Okay, so this increase in greenhouse gases is actually due to disruptions in what are called biogeochemical cycles. And we already talked about some examples of those. And so this would be like, e.g., the carbon cycle. So we talked about how carbon is released into the atmosphere, but then it can be picked up by plants. And it can be stored, the energy can be stored in the carbon. And in a long time ago, there were a lot in the tropical periods of time where the earth was warm, a lot of that carbon actually got stored underground and became our source of fossil fuels. So the burning of fossil fuels releases excessive carbon into the atmosphere. Okay. So if we look at the type of carbon emissions for the different fossil fuels, you notice that coal is actually the worst. So it is much less efficient than oil or natural gas. And so that would be like, per how much energy you get, how much CO2 are you emitting? And so that's one way that coal is considered to be dirty. Other things is that when you burn coal, you get other pollutants, and then you get coal dust. And so the dust affects us directly as people, but the CO2 that is emitted directs or completely impacts the entire planet. So you'll notice here that actually natural gas is much more efficient than coal or oil. Now, one of the problems, however, with natural gas is that we have a problem in that a lot of our infrastructure is leaking natural gas. And you might have heard of this in the past where they'll find these leaks of natural gas, and they can do they're sometimes problematic for humans on the ground. Natural gas, you can't smell it, but then they put a chemical in it that allows you to smell it. But just in general, we have these leaks in our infrastructure. And so in a given period, given area, this is just an example of an area where they mapped it to streets, and then they went around and measured the natural gas, and they found that this city, this part of the country, was actually very leaky, right? And so we're actually leaking natural gas into our atmosphere, and this is not even gas that is used for energy production. And so one of the things about natural gas is, though, yes, it is more efficient, but the problem is that the way we are using it is not efficient, in that it is leaking in different areas. And so we need to figure out how to monitor these leaks and how to prevent them. from a engineering perspective. Okay, so if we look at the change in degrees, so this is a temperature anomaly. And so this is like low, this is 0, and this is high, this is degrees Celsius. And so we see that over time, we're getting an increase, a general increase in temperature anomalies. And this is climate. So this is over time. And this is also taken at many different places on the planet. And so it could be taken over land, but it could also be taken in the water, right? And we see a general trend towards increase in temperature over time. And, I wished I can't remember exactly what these different colors are, but you could look at these graphs in your textbook. The colors, what they represent, but the red is definitely a trend line to increasing temperature over time. Okay, so other indicators that our planet is warming is the fact that sea levels are rising. So when we see the sea levels rising, and the sea levels are actually predicted to rise. There's lots of different estimates how far they're predicted to rise, but they definitely have already risen, and we have evidence of that. So if we look at the thing here, we see that it is looking at global mean sea levels in millimeters, and we see that it has increased. And the other thing that we see is the melting of ice. So this could be in ice sheets, like you see in the Antarctic, but it could also be glaciers. So I think somebody mentioned previously that in one of our discussion sessions in class, that the glaciers in Glacier National Park are declining dramatically, and we might actually be within our lifetime have a Glacier National Park that doesn't have any glaciers. And so this is just an example of showing the glacier receding over time. We also have a third thing that is happening, and this is a change in the seasons. So specifically, an earlier spring and a later winter. And so the study of seasons is actually called phenology. So this is the study of seasons. Okay. So here we see the days of the year. And so we notice that in 89 and 1990, we see that there's a much earlier spring and a much later fall. So we also see that if we look at the spatial average of the amount of green that is present, we also see that it is greener. And so this means that there is more plant growth. And this leads to a greener environment, so a greener surface, which is something that we can measure by flying over a given surface and looking at its reflective value. Okay, so we can do statistical analysis, and there's actually quite a bit of discussion of this in your textbook. And we can also run models. And so what you have been doing in SymBio is a very simple model. The climate change models are more robust, and they take into consideration more factors and they probably are, run and manipulated in a more precise fashion. So when we look at this statistical analysis and we look at this would just be under natural circumstances. If we were just looking about the changes in the tilt of the planet and the amount of energy reaching our surface, we would see that there was just these in green, this is the fluctuations that we see. And so that's the amount of like just natural variation that we should see. And we notice that just by looking at the tilt of the planet and its orbit, we cannot explain the increase in temperature over time. Then if we add the levels of CO2 in the atmosphere, and so how CO2 would affect the climate, we can see that the model does generally show a little increase, right? So if we add in the CO2 emissions that we are emitting, we see that it follows more clearly what we are actually observing as in the change of the climate. Excuse me. And then if we kind of put them together, then we see that those put together with the way that our climate, our orbit is, and the way that our CO2 and our other emissions, we see that actually follows the model more carefully. And you'll notice that there's actually kind of this decline here, and then it goes up. So there's kind of like a up, and then a step and an up. And this is actually due to, like, again, when I mentioned that we were having an industrial revolution where we were producing lots of and emitting lots of aerosols into the environment, that is what kind of led to a leveling off of the temperature right there. So that can also be, that leveling off can also be explained by anthropogenic models. That's because, and then in the 1970s, we enforced all these Clean Air Acts, and that actually led to the steep increase in temperature over time. Okay, so here's another just example of that, and this just shows that the model, the temperature over time, and then the forcing. So that would be all the factors that are affecting whether or not we are getting rid of the heat that is reaching the surface of the planet. Okay, so let's talk a little bit about carbon emissions, and we can talk about the variation depending upon the industrialized world or the developing countries. So what we see is the developed or industrialization in developing countries leads to a greater affluence. And so affluence is actually just kind of a measure of how much materials and energy per person uses in a particular society, right? And so what we see is that big countries, big developed countries, are the main emitters of the greenhouse gases. Actually, not necessarily big, sorry. Developed countries are the main emitters of greenhouse gases. So in your textbook, they have some graphs that show this. Okay. So if we looked at the average amount of CO2 that is emitted per capita, which means per person, is per year, it is 4.7 metric tons of CO2 emitted. And so this takes into consideration like what you buy, right? What kind of house you live in, et cetera, how much energy you use. And so you notice that United Arab Emirates, they have a high standard of life, right? And they rely upon fossil fuels extensively, and because of all their oil fields. And so they have a high emission rate. But if then we look at these other ones like Australia and United States, so we rank 5th in CO2 emissions. And then if you look at China, China is a pretty big country, but people don't have as much stuff in China. And so they're, in Brazil, for example, so their amount of energy used per person is and released, and the amount of CO2 released is lower than in the United States. So again, this is just another way to look at carbon emissions overall in terms of the United States and China. Right? So China overall actually has more people. So it is actually emitting more CO2 than we are because we have fewer people, even though we are emitting a lot more than China when we're talking about per person emission. And then this has to do with this high population versus low population, and then high efficiency. So if you have a country that has a low population growth and low economic growth, but was very efficient, then this is actually going to be a slow, right? You're going to actually have a little bit of CO2 emissions, and then it's going to drop off. But if you have a population that's rapidly expanding, so it's growing, right? And you're utilizing like coal for energy, so it's low efficient, and you're starting to produce things like cell phones or cars so that everybody can have one, then your CO2 emissions in that particular country are going to increase. Okay, so there are some feedback mechanisms, and we've talked about feedback mechanisms in systems. And so remember that a negative feedback mechanism helps to maintain a steady balance. Balance. So a good example of this would be the idea that as we increase CO2, we could actually increase the productivity of the plants on the planet. So the rainforest would grow more, even our crops might grow more, and then that would reduce the CO2 in the atmosphere. Okay, so let's say we increase the CO2 in the atmosphere. This causes more or greater growth in plants. And so they're taking CO2 out of the atmosphere. And so this would actually decrease CO2 in the atmosphere. Right? So if we can grow more plants, maybe we could decrease the CO2 in the atmosphere. So that's an example of a negative feedback mechanism that might work in terms of climate. We also have positive feedback. Which are actually a little bit scarier because these do not maintain a steady balance. Okay, so as we increase CO2 in the atmosphere, this actually leads to the melting of ice. And this melting of ice actually decreases the amount of energy that is reflected back into space. So this decreases the amount of energy reflected back into space. So this actually increases temperature. And this process of reflecting, the ice being able to reflect the back into space, that is called albedo. Okay, so that's the albedo effect. Okay, so as we increase temperatures, this increases melting of the ice. Right? And so you get this positive feedback, and the melting of the ice could raise the sea levels, but the warming of the atmosphere could also lead to the release of more gases into the atmosphere, specifically methane. And so another example of this increased temperature, this could increase the melting of the tundra, which increases, I have a lot of arrows here, which increases the release of methane, which I mentioned before, right? And then this increases the temperature. So that is another good example of a positive feedback. So an increased temperature increases the melting, which releases the methane, which increases the temperature. And it just has this cascading effect. And so we really don't know how these positive feedback mechanisms are going to play out in the next few decades. So in your book, they have these mechanisms, and positive is the positive and the negative is the negative, right? So the temperature decreases the surface of ice and snow. That decreases the albedo effect, and that increases temperature. And then human activity increases CO2, which increases temperature, which increases evaporation of water from the ocean. And water is actually another greenhouse gas, which we haven't talked about. But that water, when you have clouds forming, that can sometimes influence temperature in terms of holding temperature in. So we all know this, because when it's a cloudy night and it's been a hot day and the clouds roll in at the end of the day, we know that it's not going to cool off that night because the clouds are holding the heat in to the surface of the planet. Okay, so we can talk about some of the impacts of climate change, and some of these we don't know if all of them are going to occur or how bad or how different our environment is going to be. But one of the things that's going to happen, because we know that this happens when natural climate change happens, when natural ice ages happen, is that we're going to get the moving of biomes and the extinction of species. So the distribution of plants on our planet is not constant. And so you probably have heard of that, like there's deserts now, and then you see that there's fossils of tropical plants in the desert. And so at one point, that desert was a tropical swamp, for example. And we see, evidence of lakes on the fossils of marine organisms on the tops of mountains. And so the distribution of biomes is not constant, but it generally changes slowly over time. So when we're talking about naturally, so natural rate, we're talking about 10,000s of years, right? So we're talking in the tens of thousands. So like it might go from being a swamp to a desert, but that might have taken 60,000 years for that to happen, right? And so in instances of that, animals can change, right? Plants can change. They can evolve in response to that. So our current rate is much higher, right? So the current change So what is likely to happen is that there's not enough time for animals and plants to adapt to the new conditions. Okay. So that is what is going to lead to the extinction of the species. So there's been some estimates about like how many species are going to be extinct. And when they do these estimates, they separated out the terrestrial versus the aquatic. And so they estimate between 9 and 52% of terrestrial species will go extinct because of anthropogenic climate change. So they call this the 6th major extinction event. So when we look back historically, you know, there was the extinction of the dinosaurs, for example. So that was believed to be due to an asteroid that, when it landed, put a bunch of stuff into the atmosphere and actually cooled the climate dramatically. And so that was another climate-induced extinction event. But so we're in the 6th major extinction event, and species are already going extinct because of climate change. When we talk about climate change, we can also talk about changes in the seasons. And so oftentimes plants and animals are in sync. Oops, animals. And so we can think about this in terms of flowering, the production of flowers and pollinators. So maybe the flowering of the plants depends upon light. So if there is no change in the amount of light, then they're still going to flower at the given period of time. But maybe the pollinators are arriving early because of a change in temperature, because the springs are earlier. And so then the pollinators and the plants aren't in sync. And this change in the season could lead to problems ecologically in other systems. Okay, so that's just an example. Our food supplies might shrink. Not just because of our pollinator problem, but because generally of changes in precipitation and temperature. So the examples that your textbook use include flooding, right? So if we have excessive flooding, that could take out farmland when the plants are growing, and then that could lead to a reduction in food. And then we have periods of droughts, right? So maybe certain areas of our environment are going to dry up and not actually be sustainable. So I say that they may shrink because we have been very, very successful in changing our plants and breeding new breeds of plants, new strains of plants that can survive in different habitats. So perhaps through technology, we are able to get new plants that are able to grow. And also because of that idea that when you increase CO2, well, that gives there's more CO2 for the plants to suck out of the atmosphere and to use in growth. So CO2 levels might actually increase the productivity in some plants. Okay, so there's some controversy over, well, and most people think there's going to be some major problems with our food supply. Okay. And then the 4th thing would be sea level rise. So there's an estimate of about 0.5 meter to 2 meters by 2100. So that's in what, 80 years approximately. And if we look at how many people in the US would live within that, we have 3.7 million people in the US live within 1 meter of the high tide mark. I was recently in California and I was shocked, well, not shocked, but I was just dumbfounded to see that on the coastline, people are still building really fancy condos right at the sea level. And it's like, I just can't even imagine how you could do that, because I can't even imagine who would loan money and who would insure a house that is at sea level. So there's a little bit of probably some denial going on by people, but also of the insurance companies, that they're still possibly providing insurance on buildings that are definitely going to be flooded. So flooding also tends to not only, have this problem where these people are going to have to live someplace else, but they can also destroy the infrastructure. So when things flood, we have roads, we have power lines and other things. And so all of those, we have to decide whether or not we're going to repair them. So if you think about Hurricane Katrina, flooding New Orleans, and then the major floods that took place in New York and on the eastern coast just recently. Okay, so if we look at some examples of this, so this just shows the different biomes and their distribution 18,000 years ago versus 200 years ago. So biomes do migrate, but generally it's over thousands, if not tens of thousands of years. One problem with climate change that I failed to mention when we were talking about species loss is in the ocean. And so this is what we call coral bleaching. And coral bleaching is specifically due to an increase in the water temperature. And coral are really important animals because they are the builders of the reef system. And so they keep the reef close to the surface of the water, and they also provide habitat for other organisms. And so coral bleaching is where the coral lose their, lose their symbiotic algae, and they turn white. And therefore, they're no longer capable of taking CO2 out of the water. And so this would actually be another good example of a feedback mechanism, because the coral takes CO2 out of the water and deposit it as calcium carbonate in their shells, in the reef, in their physical structure. And if they die, then there's actually more CO2, which actually leads to greater warming, right? And actually also more acidification of the water, but that's a different issue. But that would be another example of species diversity, since that's the most diverse aquatic marine ecosystem or biome on the planet. The loss of the coral reefs are going to mean some major extinction event. And then food production, so I'm kind of skipping it through here. We can see the change in productivity expected. And so notice that Canada is going to become much more productive because it's going to have a longer growing season and it's going to be warmer. But then if you look at places like the central United States, like Arizona and New Mexico, then they're going to see a decrease in productivity. And so you can see how this is going to change in different places. We're going to get more productivity up here in Siberia, for example. Okay. And in Northern Europe, there's going to be a higher productivity, but Africa and South America and Australia all are going to be losing out on food production. So that, this is actually what's going to lead to what they call climate refugees. And so these are people that have to leave their country because, refugees, because of climate factors. And so maybe there's not enough food and people start moving to the cities, and then there's a breakdown of the government, and then there's mass migration of people out of the country, as like in Syria. Some people argue that Syria is one of our biggest climate refugee, first big climate refugee crisis, is that ultimately that whole Syrian crisis came down to a change in the climate. And then this is just the example that your textbook uses of flooding, the Mississippi River flooding, for example, and destroying crops. And then the rising sea levels. So high tide, normal high tide, but then we get these storm surges, right, which come in and inundate houses and towns that are close to the sea level. So those big storms, those big hurricanes are predicted to increase in strength. And with that increasing strength, then we're predicted to have greater storm surges. Okay, so we can talk about what could be done or what should be done to help to mitigate climate change. And so the first thing is that we could try to limit the magnitude and rate of climate change. And specifically the anthropogenic, the human-caused climate change. Okay. So this is referred to as mitigation. And it would probably be due to reducing carbon emissions. So you can have a market-based system, and this would include having taxes. So you could have taxes on fossil fuels that help to offset and actually pay for other technologies which actually might decrease emissions over time. And then you could also have cap and trade. So these are both market-based. So cap and trade is where you give permits. And so you actually sell permits. You give permits to industry that allow them, I'll put sell permits, that allow them to release emissions. Now, if those permits are expensive enough, then perhaps the company would decide not to release the emission and not have to buy the permit. So maybe they would develop new technologies for reducing emissions. And so that's all market-based. And there is such a thing as the carbon exchange. So I think it was in Chicago, the Chicago Climate Exchange, where you could actually buy emissions and sell emission permits like in a stock market. So that's all kind of market-based. And then we could have command and control. And so this is where the government specifies how much emissions can be released. So the government specifies. And we have been doing this with fuel efficiency. So it sets a standard. So an example would be fuel efficiency standards in new vehicles. Another good example just happened in California, where the California government said that new construction, new houses have to have solar panels on them. And so that would be a command and control way of trying to reduce emissions. If everybody's house has solar panels, then they're going to be using less natural gas or less electricity that's been produced by carbon, by burning carbon at power plants, like electrical power plants. Okay. So the other thing that we could do is we could capture and store the carbon. So is there a way that we could take the carbon out of the atmosphere that we have released and put it underground? Well, that happens naturally because when things get buried, organisms get buried, plant material gets buried, then it turns into fossil fuels. So the idea is can we, so this is happening up here. This is like new in the future, right? So this is sometimes referred to as carbon sequestration. Plants do it normally. They store carbon in themselves. Coral reefs also store carbon. But this would be capturing carbon and injecting carbon into the ground. Carbon dioxide into the ground. So storing it underground. So this slide here just shows attacks, right? And then this shows emissions in year-month contract. Okay, so this shows, this is again buying carbon emissions. So this would be how many contracts for carbon emissions have been bought, I guess. Okay. So this is the example of carbon dioxide capture and storage. So we capture it at power stations, and then we inject it underground, and we store it in different places underground, right? That have been where the carbon actually, the fossil fuel has been actually extracted. So this diagram actually is not in your book. Okay, so that really has not been successfully demonstrated that we can do that, but that would be a really good thing if it happens, and if it didn't cause earthquakes, and it was a stable way of holding it. The other thing I wanted to talk about was geoengineering. I thought I had an image for that, but I don't see that. Okay, go back. We're almost done here. Okay, so let's talk about geoengineering. So this would be different than carbon storage. And so what number am I on here? I think I'm on number 3. So mitigation, carbon storage, and geoengineering. So one of the ways that we could do this is that we could have technologies that aim to alter the climate. So technologies that alter the climate. Okay, so this could include increasing cloud cover. So could we somehow increase the amount of clouds in our atmosphere? And that one idea is to seed them, to put something into the atmosphere that would collect water and create clouds. Okay. We could also use mirrors, giant mirrors in the orbit of the planet. So mirrors could reflect light back to space. That would be interesting. We could also add, and this has kind of been in the news, we could add iron to the oceans. And iron is a limiting nutrient. We don't know how exactly it would work, but perhaps we would increase primary productivity in the phytoplankton. So we would have more productivity in more algae, for example. Okay. So that's one way we could respond to climate change. And then finally, another way would be perhaps just adapting. So how can we adapt to climate change? So this is not from an evolutionary point of view. This is like, how can humans change their behavior so that we can survive on in a planet that has a changed climate? How can we survive on a warmer planet? And so we could, for example, we could build seawalls, which is already happening. There's a big system being built to prevent water from inundating some of the European countries that are close to the ocean. And we can also develop treatment for diseases that might be caused by climate change. And we can develop new crops that would thrive in the new environment. So we would just change the way that we live in order to survive in a new climate. Okay, so that is the end of the climate change part. And I just have a really brief lecture on ozone depletion. And the reason why it is briefer is that this was a really good success story. So that kind of starts in 1986. So I kind of remember this whole thing happening in the news. And this is when the scientists announced that they had found an ozone hole over the South Pole. Now, ozone is actually a form of oxygen. So it is actually O3. So this is ozone. Now, sometimes you hear ozone as it refers to the ozone that is in smog. So it's found at the surface in smog. And it can be damaging to us there. Okay, so this is bad, right? But 90% of ozone is found in our atmosphere and specifically in the stratosphere, which is kind of a middle layer of our atmosphere. It's found in stratosphere, high above the earth. So like if we're reducing ozone at the surface, that's a good thing. But if we're reducing ozone at the stratospheric level, that is a bad thing. So this ozone hole looks something like this. And so this is the amount of ozone in color. And so this just shows that the blue, there's less ozone. And ozone is beneficial because in the atmosphere, it helps to prevent excessive UVB radiation from hitting the surface of the planet. So it prevents UVB radiation from hitting the surface of the planet. Not all of it, but it prevents some of it. So it absorbs the UV radiation, UVB specifically. So much will prevents much. And radiation is obviously a good thing because it's sunlight that allows for photosynthesis, but radiation also is able to penetrate into our bodies, into the cells of all creatures, and it can actually cause genetic damage. So it can cause genetic damage. So that is damage to the DNA. Okay? So this can lead to skin cancer. So even you get UVB radiation when you're tanning, and that can actually lead to an increase in skin cancer. And it can also cause some organisms that are susceptible to decrease in decline. So another big thing that it did is it's believed to have been caused amphibian declines because, oops, they have shellless eggs. So they do not have a hard shell to protect them, and sunlight can penetrate into the egg where the developing embryo is developing. And if it causes genetic damage, then you're going to see the eggs not developing into tadpoles, and you're going to see a dramatic amphibian decline. And so we were starting to see evidence that we had higher rates of skin cancer, and we were actually seeing amphibian declines as just a couple of examples of what was happening when we had the ozone hole. Okay. So if we look at the amount of ozone in measured and satellite versus our ground base, we see that it decreased during this period of time between 1973, and it actually is still decreasing a little bit today, but the ozone is starting to repair itself. The ozone hole is beginning to repair itself. And so the cause of this ozone depletion was due to a propellant that was put into aerosols, like paint cans and maybe even fire extinguishers. And the propellants are called CFCs. And these are called chlorofluorocarbons, and you don't need to know that. But these were put into, they were called the propellants in aerosol cans. They were also in refrigerants. So like in your car air conditioning and also running through the refrigerator coils, they helped to keep things cool. So what we see is that the CFCs break down ozone. And obviously there was a lot of political push by industries to say this was not the case. But a couple of things happened that made it a good thing, that it just happened to be a good decline. And that is that they developed better technology. So industry developed better technology for propellants. They could use something else that was actually easier to use and better. And so they just started to phase out the use of CFCs in the aerosol cans. So when we look at the causes and effects, oops, so I had my slides out of order here, sorry. That was my geoengineering. Okay, here, sorry. So this is the diagram that shows ozone. So this is my CFC. It gets put into the atmosphere, and then light breaks it down into chlorine. And then chlorine combines with ozone, that O3, and it breaks it down. And so the CFCs released into the atmosphere is actually what caused the ozone hole to appear and then to grow bigger over those periods of years. So if we look at the effects in annual amphibian populations, during that same time that we saw that ozone hole appear, we see that there's a trend of a decrease in global amphibian populations over that period of time. So what has happened since then? CFCs during this period of time were very high, the release of them. And then subsequently, governments got together and they started banning them, and industry got on board because it was easy for them to do because of new technology. And we were able to decrease the release of CFCs. And so today, when you look at news lines, if you Googled the ozone hole, you would see that there's some evidence that it is starting to repair itself. It's starting to get less. And we're not really too concerned about it now because we know that these CFCs are going to break down over time. and they're not going to be, it's not going to be a long-term problem. And so that is why the ozone depletion, unlike climate change, is a success story. Okay, so that's my lecture for today, and thank you very much for listening. Hope I was of help.